Section 4.6 is on a topic called related rates. And I want to start with this quote from your book. The difference between algebra and calculus is that calculus can deal with variables that change over time. So back in algebra or geometry, you learned this formula for the volume of a sphere. You're going to manipulate it and solve it and plug in something for r to figure out the v that goes with it. But you never actually solved a problem about a sphere that was actively in the process of changing its volume. But now we can imagine like somebody blowing up a balloon or making a soap bubble. The volume is changing. And we probably do, want to know how fast the volume is changing. So we can answer this if we understand related rates. Before we jump into related rates, you have to remember implicit differentiation. Remember, implicit differentiation is sort of the art of taking the derivative of an expression with respect to a variable that's not part of the expression. So we have this example, y squared plus x squared equals 17. Can I find dy dx? I can do that if I differentiate the whole equation, both sides, with respect to x. The derivative with respect to x of y squared is 2y, which is the derivative of y squared with respect to y, times whatever this dy dx thing is. 2x I can take the derivative of with respect to x, and I don't have to worry about this extra term because I'm already taking the derivative with respect to the correct variable. So I can isolate my dy dx and solve for dy dx. Notice I could just as easily have done that problem with different variables. There's nothing special about x and y. If I had p squared plus t squared equals 17, and I wanted to find dp dt, I would take the derivative of both sides with respect to t. So now come back to the soap bubble. The volume is changing. The volume is changing as time goes by. So the way the volume of the sphere is changing is with respect to time. So that's the thing I'm interested to know, the rate at which the volume is changing with respect to time. If I think about those words, I wanted to translate that into calculus notation. The rate of change of the volume with respect to time, that's dv dt. So start with our formula for volume of a sphere, and I can actually differentiate with respect to time. Notice there's no time variable in this equation that relates the volume of a sphere to its radius, but I can differentiate with respect to whatever the heck variable I want. This time I'm going to differentiate with respect to t, that's with respect to time. So the derivative of v on the left-hand side with respect to time is just dv dt equals, so the 3, which is the exponent on the r, is going to come down to the front and multiply with the 4/3 that's already there to give me a 4. The pi is a constant multiplier, so that stays. The derivative of r cubed with respect to time is the derivative of r cubed, which is 3r squared, multiplied by whatever the derivative of r with respect to time is. We just call that dr dt. So think about this though. I've got the notation all written out. What would dr dt mean? Well, if r is the length of the radius, then dr dt is the rate at which the radius is changing with respect to time. So notice that the rate at which the volume is changing is related to the rate at which the radius is changing, and that's how we get that term related rates. So let's finish up with our soap bubble. We know dv dt, the rate at which volume changes with respect to time, is 4 pi r squared times dr dt. If I happen to know that at the exact moment that the radius is 10 centimeters, the radius is increasing at 0.1 centimeters per second, I can plug this in. So I replaced r with 10 centimeters. I replaced dr dt with 0.1 centimeters per second. And I can find out that dv dt is 40 pi cubic centimeters per second. That's the rate at which the volume is changing. Since my answer is positive, I know the volume is increasing, which matches my understanding of what happens when you blow up a soap bubble and let the radius get bigger.